All right, welcome to The Explainer. This is where we take those really complex topics and, make them make sense. Today, we're jumping into something that's, well, it's absolutely fundamental in machine learning, but it's also a place where a lot of people trip up. We're talking about how we split our data.
So let's set the scene. You've been grinding away for weeks on this new machine learning model. You finally test it and boom, 99% accuracy. That feels amazing, right? You're thinking, I nailed it. But hold on. The real test, the question that actually matters, is what happens when this shiny new model goes out into the wild and sees data it's never, ever encountered before.
And yeah, the reality is often a punch in the gut. That amazing 99% can plummet, maybe all the way down to 55%. What does that tell you? It tells you the model didn't actually learn anything deep. Nope, it just memorized the answers on the test it was given. And let's be honest, a model that just memorizes, it's pretty much useless in the real world. This right here is the central problem we've got to tackle.
And that brings us to what's known as the unseen data problem. You see, the whole point of machine learning isn't just to be a star performer on the data we already have. No, the real magic, the ultimate goal, is for it to make smart, accurate predictions on brand new stuff. This power to work well on data it's never seen, that's called generalization, and it's everything. Now, when you have a model that's an A-plus student on its homework, but then completely bombs the final exam, we have a special name for that. It's called overfitting. This usually happens when the model is maybe a little too smart for its own good, or it just didn't have enough data to study from. It starts memorizing all the weird little quirks and noise in the data, instead of the real meaningful signal. It's totally missing the forest for the trees.
Okay, so how do we fix this? How do we build models that actually learn and don't just overfit? Well, the answer is a really elegant three-part solution. The standard practice across the board is to split our data into three totally separate piles. Each one has a very, very specific job to do. First up, you've got the training set. This is the big one, right? It's the largest chunk of your data, usually something like 60 to 80%. Just think of it like the official textbook for your model. This is where it does all its studying, learning all the core patterns and relationships from the examples we give it. Then we've got the validation set. Now, this is a smaller piece of data that the model never gets to study directly. This is like its pop quizzes or practice exams. We use this set to tweak the model's settings, we call those hyperparameters, and crucially, to see if it's starting to just memorize things. It's our little checkpoint to make sure our study strategy is actually working. And last, but definitely not least, we have the test set. This part of the data is sacred. It's locked in a vault, completely untouched until the very, very end. We only use it one time. After all the learning and all the tuning is done, this is it. This is the final exam. It gives us the one true, unbiased grade on how our model is going to do when it faces the real world. And what's so cool here is how you can see all their different jobs laid out so clearly. The training set is where the learning happens, but that's also where the risk of overfitting is super high. The validation set, that's our tuning fork, our guardrail. And the test set, that's the moment of truth, the final honest score. You absolutely need all three to build a model you can actually trust. So this whole three-way split thing, it seems pretty simple, right? But, and this is a big but, there's a really sneaky, and I mean incredibly common mistake that can blow the whole thing up. It can make all your amazing results, well, just an illusion. That mistake is called data leakage, and as this quote gets at, it's basically when information from outside the training data accidentally contaminates the learning process. It's like the model gets an unfair sneak peek at the answers to the test, and what you get is a performance score that's totally fake and wildly optimistic. So how on earth does this even happen? Well, the number one culprit is doing your data prep, things like scaling numbers or filling in missing values, on the entire dataset before you split it. It feels faster, it feels efficient, but trust me, it's a catastrophic mistake. Here's a perfect example. Let's say you scale all your data to be between 0 and 1. To do that, the computer needs to know the absolute minimum and maximum values in your data. If you do this on the whole dataset, that means the min and max from your test set were used in the calculation. So information from the final exam has just leaked into the study material. Your model now has inside information, and its performance score is going to be a lie. Okay, so how do we dodge this bullet? Thankfully, the fix is actually super simple. It's a golden rule, it's non-negotiable, and every single person working in this field needs to have it tattooed on their brain. And here it is, the golden rule. You have to fit your data preparation on the training data only. That's it. You split first, then you do your prep work. Any tool you use, whether it's for scaling or something else, has to learn what to do based only on that training set. And this is the correct way to do it, step by step. Step 1, split your data. Don't touch anything else. Step 2, you fit your data prep tool, let's say it's a scaler, using only the training data. Step 3, you take that exact same fitted scaler and use it to transform both the training data and the test data. See the difference? Now the test set stays totally pure and you get a real, honest-to-goodness measure of your model's performance. Look, following this rule isn't just some academic exercise to get a slightly better number. This is about the fundamental integrity of your entire project. It's literally the difference between building an AI system that you can trust and, well, building a total house of cards. And just think about the stakes here. A model you think is 99% accurate, but in reality is only hitting 55%. That can lead to absolutely disastrous decisions in business, completely wrong scientific conclusions, and it can totally destroy any trust people have in your work. Data leakage isn't a small mistake. It creates a false sense of security with very, very real consequences. And if you think this is a rare problem, think again. This number just shows how big of a deal this is. A 2023 study found that data leakage probably messed up the results of at least 294 scientific papers. We're talking about overly optimistic results that might have compromised years and years of research. So no, this isn't just some rookie mistake. It's a huge systemic problem. So let me leave you with this. The next time you get a crazy high accuracy score and you're ready to pop the champagne, just pause for a second. Ask yourself this one critical question. Is this performance real or is it just an illusion? Because honestly, the answer to that question is the very foundation that all trustworthy AI is built on.